Example 7 deals with compound interest. And compound interest is another exponential growth situation, but it has a very specific look about it. So let's have a look at this. On his first birthday, Howard's grandfather put $5,000 into a money market savings account that earns 3.4% annual interest. Based on this answer, the following. A, if the interest in the account was compounded annually, what is the effective interest rate? And how much will the account be worth when Howard turns 18 years old? B, it's the same sort of situation except it's compounded monthly. And then C, it's compounded continuously. And so let's look at these individually. When you deal with compound interest, the formula is A equals P times the quantity 1 plus R over N to the NT power. This represents the accumulated amount. That's the amount that's in the account or whatever the situation is after this period of time has gone by. P is the principal, which is the beginning amount. Sometimes this will also be represented as A sub 0, and you'll see that in exponential functions too, which stands for the starting amount. Keep that in mind. It's the same idea. It stands for the principal or the beginning amount. R is the interest rate expressed in decimal form. So the 3.4% will be converted into decimal form. The N is the compounding period. Basically, when it says compounded annually, that represents that N is going to be 1. Other words like semi-annually, that would be N being 2, quarterly, N equaling 4, so forth and so on. You have a list in the top hat as far as like your notes go about what means what. And of course, T is the amount of time. In most compound interest formulas, in situations, that's going to be in years. So in this situation here, you know that the principal is $5,000. You know that R is 0.034. In this case, N is going to be 1. And in a lot of cases, it might be a good idea to simplify this expression here. So in this case, it's going to be 5,000 times 1.034 to the T power. And now that represents that you're going to have 103.4% of the original amount every, in this case, year. So the effective interest rate for this is still 3.4%. Because really the compounding doesn't really change anything. That's 3.4% every year. I'm only applying it once in that year, so it's not going to have any effect on the interest rate. Other compounding periods are going to change what this is. And then how much will be in the account after he's 18 years old, which again means that 17 years have gone by. And that means you just put in 17 for T, and you get about 8,827.12 or $8,827.12. Keep in mind, you're often not going to be told what to round money to unless you want the nearest dollar. When you're not told how to round it, keep in mind we go to decimal places for money, dollars and cents. So when you deal with the next one, part B, and it says compounded monthly, the only thing that's going to change between the things we had before is that the value of N is now 12. It's being compounded 12 times a year, which means that you're taking your interest rate, you're splitting it in 12 pieces and applying it 12 times during the course of the year. Here's why this makes it a little bit different as far as the effective rate goes. Yes, you have 3.4% annual interest yearly. However, if you evaluate this, you get about 1.034534869, which is about 103.4534869%. That means that it's growing by 3.45 and some change percent, or about 3.45%. So you can see that compounding actually gives you a little bit more interest as a result because you're earning a little bit more than 3.4%. And if you're talking about bigger money values, that can make a significant difference. If you're talking about like, small money values, probably not much. It's this that we're going to be using for each year. And so again, when he's 18 years old, The time t would be 17, so you put a 17 into this, and you would get about $8,905.07, which is certainly more than you saw in the previous example. Now, they bring up a situation that's more theoretical than anything, because usually compounded interest, it's done during periods of time. You usually don't see many that go to monthly. That's usually, sometimes you'll see it done semi-annually or quarterly. Monthly, maybe here and there. Daily, you don't really see a whole lot. But compounding continuously is certainly a different situation. They bring up this situation to basically bring in the exponential base of e. What it tends to be used for in some cases is to figure out what is the maximum effective rate you could possibly have through compounding. Because compounding continuously is really a situation that it's not really feasible to happen. It means that for our purposes, if we were looking at the regular compounding formula, we would be taking that interest rate of 3.4%, dividing it into an infinite number of infinitely small pieces, and then applying it an infinite number of times. You really can't do that. But the formula, when you see compounded continuously, is going to be different than any other compounding periods. And that's when you're going to see A equals P times e to the RT power. And again, P might be represented as A sub 0 in some cases. That's okay too. But the meanings of A, P, and R, and T are all the same, except now you're just going to have the exponential base of E, which is about 2.71 something or other. And so here, all you're going to be doing is substituting the values in. Your principal is 5,000. Your interest rate is 0.034. Again, it's represented in decimal form. And all you're going to do for this is, that e to the 0.034, that's going to help you get your effective rate, because you're going to see 1.034584607. And if you look at this, it's about 3.458% or about 3.46%. So that's the most that you're going to probably get up to through compounded interest. It's going to change it by 0.06% max as far as an effective rate goes. And then you're just going to plug in the 17 again to get the value, and you end up getting about, when you do this, about $8,912.35. It's still a little bit more than the previous one, not much more. Not as big a difference as when we went from compounded annually to monthly, but it's still somewhat of a difference. So that's our talk about compound interest. That's the end of this problem in this video. If you have any additional questions, please make sure to bring them up during our class session.